Evaluating large language models, it's a huge challenge, isn't it? Getting them to produce stuff that's not just plausible sounding, but actually, good.
Absolutely. Good, reliable, aligned with what you actually wanted. And then the really tricky part is building systems that can judge that quality reliably.
Especially for complex outputs, right? Things with reasoning steps, nuances,
Yeah,
and then using that judgment to make the models even better.
yeah, that's definitely one of the frontier areas in AI. The traditional ways we evaluate and give feedback, they kind of run into trouble when the outputs get really subtle or complex.
They don't really think deeply about the evaluation itself.
Exactly. They lack that ability to sort of deliberate. Which brings us to some really interesting new work we've been digging into.
Ah, yes. From researchers at Microsoft, Tsinghua, and Peking University, we looked at some research notes and a preprint.
Right, and it introduces something called reward reasoning models, or RRMs.
RRMs.
It's a pretty fundamental shift in how these evaluation systems might work. So our plan today is to do a deep dive into what RRMs are.
Focusing especially on the innovative bits, the academic details of how they work and why they're getting these results.
Exactly, giving you that shortcut to understanding this edge of AI development.
Okay, so before we get to RRMs, let's make sure we understand the problem they're solving. We talk about reward models, RMs, used in things like RLHF. What's their usual job?
So think of a standard RM as the critic in the system. An LLM generates a response, maybe two responses, and the RM gives a score or a preference.
Reward signal.
Yeah, a signal saying this one's better or this one gets a score of X. And that signal is then used to tune the main LLM, nudging it towards better outputs later.
Got it. They provide that scalar feedback for the RL process, but you mentioned limitations.
The big one highlighted in this RRM research is how they use compute. Standard RMs tend to use, well, basically the same amount of computational effort for every single evaluation.
Regardless of how hard the evaluation is?
Pretty much. Like spending the same brain power checking 1 + 1 years as verifying a complex bit of logic, it's just not efficient.
Right, that doesn't sound right.
The paper calls it an open challenge, how to effectively use test time compute. That's the resources available when the RM is actually doing the judging.
And standard models just don't adapt that compute use.
Nope. They don't really have a mechanism to say, hang on, this one's tricky, I need to think harder. And that limits their ability to judge tasks that need, careful reasoning or check in multiple steps.
Which is exactly where we need better evaluation for modern LMs, because those are the tasks we want them to do.
Precisely. Evaluating complex reasoning, well, it requires reasoning by the evaluator. If your judge can't deliberate, it can't give good feedback on deliberation.
Okay, problem clear. Standard reward models don't reason about their judgments. So the big idea with reward reasoning models, RRMs, is they do.
That's the core innovation, yes.
Yeah.
The paper says they're specifically designed to execute a deliberate reasoning process before generating final rewards.
So the reasoning happens inside the reward model itself.
Exactly. It's like applying chain of thought reasoning, but internally for the evaluation task. Instead of just mapping inputs to a score instantly, the RRM generates intermediate steps, thinking steps.
Like it's writing out its own little evaluation argument internally.
Kind of, yeah. You can see it in Figure 2 in the paper, this distinct long reasoning block within the RRM. It contrasts sharply with simpler models that just have direct path.
So it might internally think, okay, response A answers the question directly. Response B adds some nuance but misses a constraint. Comparing them, A is better because B failed on the constraint. Something like that.
That's the gist of it. This internal deliberation lets RRMs leverage additional test time compute for complex queries. If the judgment isn't obvious, it can spend more cycles thinking it through.
It reframes reward modeling itself as a reasoning task. That makes a lot of intuitive sense.
It really does. An evaluator for reasoning should be able to reason.
But, okay, the tricky part must be training this. How do you teach a model this internal evaluation reasoning? You can't just ask thousands of people to write down why they preferred chatbot answer A over B, right? That data doesn't exist at scale.
Right. That's the next big innovative piece. They introduce a training framework called Reward Reasoning via Reinforcement Learning, or RRRL.
RRL. Okay, reinforcement learning. How does that help when you don't have the reasoning steps to supervise directly?
The clever part is that RRRL lets the RRMs self-evolve their reward reasoning capabilities without needing those explicit reasoning examples.
Self-evolve, how?
It's pure RL. The RRM's internal reasoning process generating those intermediate steps is treated as a sequence of actions. The model takes these actions to reach a final judgment.
And the reward signal tells it if the final judgment was good, even if it doesn't know how it got there.
Exactly. And the reward signal itself is super simple. Basically, +1 if the RRM's final preference between two responses matches the known correct preference, and -1 if it doesn't.
That's it. Just getting the final answer right is enough to teach it how to reason internally.
Apparently so. The paper argues that this simple rule-based reward can effectively supervise the policy models to develop reasoning patterns that lead to correct final judgments. The RL process encourages reasoning strategies that consistently lead to the right answer.
Wow. So it learns what kind of internal thinking works best just by trying to get the final comparison right. That's elegant.
Very. It neatly sidesteps the need for explicit reasoning data.
And technically, what are these models built on?
They use DeepSeek R1 distilled Qwen models as the base, and the RL training used group relative policy optimization, GRPO. Pretty standard RL techniques, but applied in this novel way.
Okay, so the core RRM reasons about two responses in detail, but often you need to pick the best from, say, 16 options, like in best event sampling. How does that work?
Yeah, they address that with what they call adaptive multi-response rewarding strategies. You use the core pairwise RRM, but structure the comparisons cleverly.
What kind of structures?
Two main ones. First, an ELO rating system.
Like for chess rankings.
Exactly like that. You run a round-robin tournament. Every response gets compared pairwise against every other response using the RRM.
Ah, okay.
Based on all those win-loss results, you calculate an ELO-style rating for each response.
That sounds comprehensive. Gives you a score for every single candidate.
Yep, a full rating.
Yeah.
Great for generating detailed preference data for further LLM training, like RLHF. The only catch is its ON comparisons, which can be a lot if N is big, though they mention you can sample pairs.
Makes sense. What's the second strategy?
That's the knockout tournament. Much more efficient.
Like a sports bracket.
Exactly. Responses are paired up. The RRM picks the winner. Winner advances. You keep doing that until you have one overall winner.
Single elimination.
Right. It needs only N1 comparisons total, so it's ON computationally, and it finishes in O log N sequential steps. Much faster if all you need is the single best response.
Like for best of N, where you just want the top pick.
Precisely. ELO for ranking, knockout for picking the winner fast.
I think I saw something about majority voting, too. How does that fit in?
Yes, that connects back to using more compute for accuracy. For any single pairwise comparison, whether it's in the ELO or knockout setup, you can actually run the RRM multiple times, say 5 or 16 times.
On the same pair of responses.
Yes. And then you take the majority vote from those multiple runs as the final decision for that pair. It uses more compute in parallel for that one comparison, but makes the judgment more robust.
Got it. So you can spend more compute per decision with majority voting, or structure the overall evaluation differently with ELO versus knockout. That offers flexibility.
And they showed this works. Figure 5 demonstrates that for best of N on the math dataset, simply doing more pairwise comparisons boosts the accuracy of picking the correct best answer.
Directly using that parallel compute.
Right, and Table 5 confirms the trade-off. ELO generally gets higher accuracy, but knockout is significantly faster.
That makes sense. But what about the other way to use compute you mentioned earlier, the sequential scaling? Can it actually improve just by thinking longer on one comparison?
This is one of the really cool findings, I think, is shown in Figure 6. They let the RRM models run for longer thinking horizons.
Meaning they generate more steps in their internal reasoning chain.
Exactly. For a single pairwise judgment, they just let it run longer, generate more internal thought steps.
And then help.
Yes. Consistently across different model sizes, 7B, 14B, 32B, letting them think longer improved accuracy on the reward benchmark.
Wow. So without changing the model or the data, just giving it more time to process a single hard case makes it better.
That's what the results show. It's direct evidence that the reasoning process itself is valuable and can be scaled sequentially. It gives you this flexible way to trade compute for accuracy at test time.
Just turn up the thinking time knob for harder problems. That's a powerful capability.
It's a direct payoff from designing the model to reason in the first place.
Okay. Innovative concepts, clever training, proof it uses compute adaptively. How does it stack up overall? Are these RMs actually better evaluation models in practice?
The performance looks really strong. On standard benchmarks like RewardBench and PandaLM, they're competitive with top models like GPT-4o and Claude 3.5 Sonnet.
Competitive with those giants.
Yes, and they consistently outperform other strong open-source reward models, especially in the reasoning categories of these benchmarks.
Reasoning specifically.
That seems to be where they really shine. Table 1 shows the RM32B model getting 98.6% accuracy on the reasoning tasks in Reward Bench.
98.6, that's almost perfect. That's
Yeah.
incredible for judging reasoning quality.
And to really isolate the benefit of the reasoning process, they did an important comparison. They trained baseline models called direct judge, using the exact same data, but without the explicit reasoning step baked into the RRM architecture and training.
So same data, same base model size, just no internal reasoning objective.
Right. And Table 1 shows a substantial performance gap in reasoning between the RRMs and these direct judge models.
Ah, so that gap directly points to the value added by the RRM's internal deliberation. The thinking really does make the difference.
It seems so. It's strong evidence for the architectural choice.
What about using them for practical things, like picking the best answer out of many, best of n?
They tested that on datasets like MMLU Pro, Math, and GPQA, what they call preference proxy evaluations. And RRMs surpass all baseline models in picking the best response from the set. That's in Table 2.
Better than other models at picking the top answer.
And using that majority voting technique we discussed boosted the performance even further.
Okay, and just straight pairwise comparison, is A better than B?
There, too, they achieved state-of-the-art accuracy on those same challenging datasets, MMLU Pro, Math, GPQA, according to Table 3. The RRM32B even outperformed much larger models, like a 70 billion parameter J1 Llama model.
Wait, a 32B RRM beat a 70B model on pairwise accuracy?
On those specific benchmarks, yes. Figure 1 visually shows how RRMs seem to offer better performance for their size compared to many existing reward models.
So they're not just good, they're efficient too, punching above their weight class parameter-wise.
It suggests that the architecture and the reasoning capability itself provide significant leverage.
Okay, the ultimate proof is often downstream tasks. Can these better evaluation signals actually help train other LLMs to be better?
Yes, and the results here are also very positive. They use the ELO ratings generated by an RRM to train another model, a DeepSeek R1 Distill Qwen 7B, using reinforcement learning with unlabeled data, or RLUD.
So using RRM scores as the reward signal in RL.
Correct. And figures 3 and 4 show steady performance improvement on GPQA and MMLU Pro for the model being trained. The RRM signal was effective for guiding the RL process.
Good. What about other post-training methods like DPO?
They tested that too. They trained Qwen 2.57B models using DPO, comparing preference labels generated by RRMs, both 7B and 32B versions, against labels generated by GPT-4o.
Okay, RRM labels versus GPT-4o labels. What happened?
The models trained with RRM labels achieved higher arena hard scores than the models trained with GPT-4o labels. That's in Table 4.
Higher scores than using GPT-4o. Wow, that's a very strong result. It suggests the RRM's judgments, at least for these tasks, might be even more useful for alignment than labels from one of the top proprietary models.
It's definitely a significant finding. It underscores the quality of the feedback signal generated by the RRM's reasoned evaluation process.
Let's get academic again for a second. Did they actually look inside the RRM's reasoning? What does that self-evolved thought process look like?
They did. They analyzed the patterns in the reasoning traces generated by the RRM32B model and compared them to a baseline model trained without the explicit reasoning goal.
And what patterns emerged?
Figure 8 shows it quite nicely. The RRM32B tended to use more tokens associated with transition, reflection, and comparison patterns.
Fewer direct breakdown patterns compared to the baseline.
Exactly. The baseline was more about just breaking down the input, whereas the RRM seemed to spend more time transitioning between points, reflecting on the criteria, and explicitly comparing the responses.
That sounds, well, more like how a careful human analyst would evaluate something complex, doesn't it? You don't just list facts, you compare, contrast, reconsider.
That's precisely the interpretation they offer, backed by case studies in Table 6. They describe the RRM's process as more iterative, involving self-reflection and comparative analysis.
Which leads to better judgment.
It seems to enable more detailed analysis and interpretation of the instructions, and ultimately, more accurate comparative judgments. It shows how the RRRL training shaped the internal evaluation strategy.
So that simple +1-1 reward signal really did push the model towards a more sophisticated, human-like evaluation process internally. Amazing.
It really highlights the power of RL to shape not just what a model outputs, but how it gets there.
Okay, let's try to quickly summarize the main contributions here.
Sure. So first, the core idea. Reward reasoning models that do explicit internal reasoning, which allows them to adaptively use test-time compute.
Then the novel training, the RRL framework that lets them learn this reasoning without explicit examples.
Right. Then the strong experimental results, competitive or state-of-the-art benchmark performance, especially on reasoning.
Outperforming baselines and even larger models sometimes.
Demonstrating effective scaling with both parallel compute, like more comparisons or majority voting, and sequential compute, just thinking longer.
And proving effective in actual downstream LLM training, both RL and DPO, even generating labels that led to better results than GPT-4o in one case.
And finally, the analysis showing how the reasoning process differs and seems more sophisticated.
Plus, crucially, they've open-sourced the models on Hugging Face, which is great for the research community.
Yes, you can find them under reward reasoning on Hugging Face.
So pulling it all together, these RRMs feel like a really significant step, moving from reward models that just assign a score to ones that can actually reason about quality and adapt their effort like a human expert might.
It's definitely a move towards AI evaluators that have a deeper, more procedural understanding of why one response is better than another.
Which leads to our final thought for you to consider. If we can now train AI systems to reason about quality and alignment in this more deliberate way, maybe even using these self-evolution techniques, how could that change the game? Could we see future AI systems using ROM-like components to evaluate and refine their own work internally? What happens when an AI can truly reason about what makes its own output good? What possibilities does that unlock? Something to chew on.